Well, here's the standard of projections for 2100. That's the IPCC models. Low emission there, high emission there. Doesn't look too bad. Those are fairly gentle looking curves. But again, you need to put them in an Earth system perspective. So if we use this same graph here with the 2,000-year perspective and put that on, it looks like this. So it's, again, an extremely sharp spike. So remember, this is 1900, 2000, 2100, looks like that. So this is why scientists, Earth system scientists, are exceptionally concerned about what this actually represents. We go back probably 100 million years with good enough records to interrogate, has this happened before? And we can see only 2 times in the last 100 million years when we've seen anything close to this, not quite as sharp as this. One was when the meteorite hit about 65 million years ago and wiped out the dinosaurs. That was a big shift in the opposite direction from all the dust thrown up. But then we saw a temperature spike about 56 million years ago. And that was a really interesting one because it was driven by carbon being shoved into the atmosphere from the ocean, from sediments. And we don't know what triggered it. That's still a mystery. But once it got going, it was unstoppable. And temperature got to be 5 or 6 degrees higher. And there was a mass extinction in the ocean during that time. So the Earth has seen changes vaguely like this before, and they haven't had good outcomes for the biosphere. So that's why we're really worried about missing the Paris target, which is there. So I think we're pretty much committed, and you have to be really brave to say we're going to make 1.5, because we're already at 1.1, 1.2. We have a shot at 2, because I'll show you in a minute, we got no time left. We got to act now, start acting now if we're going to get there. Of course, if we don't get there, we could go to 4, perhaps even 5, by the end of this century or certainly in the next century. And that's a huge challenge, not just for the natural world, but for humans to deal with. And some people think a worst case scenario is we could get a collapse of the civilization that we know today. So from an Earth system science point of view, climate change looks very different than from the normal point of view. So the implications are, if we can meet the Paris target, there's a chance we can stabilize the climate and maybe slowly, over centuries and millennia, cool it back down. This is probably survivable, although it's going to be a rocky road. But I suspect we are clever enough and robust enough to survive that. Not everyone, not the poorer countries, but by and large will do this. However, the problem is, if you go much above here, there's a chance, a risk that you're not going to stop there. You're going to go all the way there. And that's because of so-called tipping elements in the Earth system, which may just put a bifurcation, a fork in the road. And once you start on that road, you don't get on this one. And the reason for that is these elements in the system, parts of the Earth system, that can change suddenly with a bit of a push. That's a tipping element. So they come as 3 different types. Biomes, that's big parts of the biosphere like the Amazon forest or coral reefs. Changes in atmospheric and ocean circulation. And this one's getting really important now, and that's melting of polar ice. Because that can really raise sea level, huge issue for a country like New Zealand. And the more we learn, the more we're realizing we actually should put another one here over in East Antarctica. Because the biggest glacier there, the Totten, looks like it's much less stable than we thought even 5 years ago. So these are the sort of tipping elements that are there, and say, well, at 1 degree, is anything happening? The answer is yes. Amazon in the last decade has had 2 very big droughts and fires. It's lost a decade worth of carbon that's taken up. So we're getting extra carbon into the atmosphere from that. Permafrost, that's frozen carbon in the soil up in Siberia. That's starting to bubble out in small amounts at the moment, so it's not a big effect yet. But depending on whether we hit 2 degrees or go higher, we could lose quite a bit of carbon from that area this century. Remember that human emissions are about 10 billion tons, so that upper limit is about 25 years worth of human emissions of extra carbon. That in itself would blow the carbon budget. Remember, we had 225 billion tons for all of humanity till we decarbonize. If we destabilize this area in its own could blow the carbon budget. So these are big items in the Earth system that we're thinking about. Arctic sea ice, that's the floating ice. That's dropping off at a very fast rate, faster than the models predict it will. I think that's tipped already in terms of we're committed to lose it entirely in the summertime, probably in a couple of decades. And of course, we've said that coral reefs have tipped already. Polar ice. Polar ice is really important, Greenland and West Antarctica down here, because they're land-based. And if they melt, they raise the sea level. So the projections now are that there may well be a tipping point for Greenland that we could hit this century. 2 to 3 degrees, Greenland could tip. And that would mean eventually about 7 meters of sea level rise. You can imagine what Wellington would look like with 7 meters higher around that waterfront. It's not a nice future. And as I said, we're almost certain that coral reefs have already tipped. So these are big changes in the Earth system at 1 degree or so. And they are sort of saying, look, if you really want to push this system beyond 2 degrees, you're going to tip a lot more of those. And once you start tipping them, as there you can see, there's the Paris target. Several of those tipping elements sit there, but when you start tipping them, they actually push the temperature up to where you start tipping others. And you get what we call tipping cascade. This is typical of a single complex system, is it wants to exist in stable states, but when you start destabilizing it, it has its own internal mechanisms to move to another state. And we know that a 5-degree warmer world is very stable. It's been there for a long time. It'll eliminate all the northern hemisphere ice and it'll eliminate roughly half of the Antarctic ice sheet. So the problem is you just don't want to get this thing going. You want to avoid that. So that's the difference between a 2-degree world and possibly a 3-degree world, is that tipping point may be triggered somewhere in there. So from an Earth system science point of view, there's an even better argument for the Paris 2-degree target than just, well, you have a few more impacts at 3 degrees. Well, you may actually tip the whole system between 2 and 3. The other thing that we Earth system scientists look at are long time frames. This is the last 10,000 years of a very warm, stable period that has allowed humanity to develop agriculture, settlement, civilization. But for any of the climate scenarios, this one just under this first blue line is the Paris 2. So that basically is the 1.5 to 2, the lowest one. But notice over 10,000 years, the temperature doesn't come back down. And that's because of the long-lived gases in the atmosphere. The fact that if we allowed nature to bring them down, they'll bring them down, but on the order of about 100,000 years, not 10,000 years. So wherever we land up here, we're stuck. So you got to think very carefully of what sort of world you want your children and grandchildren to live in, because generations into the future are going to be stuck with that. So it's the irreversibility is again, not talked about much, but this is a one-way road, people. We're not going to come back from wherever we set the climate. Now, the crunch. I hope I've convinced you don't want to go beyond the Paris target. That's really, really risky. So how do we make sure we don't? Well, again, we go back to this budget. And how do we cope with this budget? Well, let's look at our roughly 225 billion tons that we can burn. These are 3 different lines that all stay within that budget. But notice how sensitive they are to when you start going down. If we could have got going down last year or the year before, we have out to about 2045 before we completely decarbonize. And you can imagine 3 decades working hard. We could do that without too much economic disruption. It would be tough, but we could do it. But waiting till 2020, which is the next sort of fork in the road, that's this yellow one, we're going to decarbonize by 2040. Now we're looking at the 2.5 decade. That's tough. We might be able to do it. But if we miss the 2020 and wait for 2025, it's basically impossible. You've got to decarbonize in 1 decade, and it's just technologically and economically not possible. So this is why it's really, really critical that although the decarbonization time looks a little bit far out in the future, the time we have to commit to it, have a plan, and have policies is only 3 years, 2020. That's a term of a government, or even less in some countries. So it's hugely important that pressure gets put on now. You've got an opportunity in New Zealand. You've got an election coming up very soon. And as we've talked about with my colleagues at Victor, I haven't heard much about climate change from the snippets I've heard in the election. At least in Australia, it gets in there because energy is such a toxic issue, you can't avoid it. But here it's different because energy may not be such an issue with hydro and geothermal. But it's hugely important for New Zealanders to realize that every country has to do its share to get onto this yellow curve. And if we don't, it's going to be virtually impossible to meet that Paris target. A few closing comments then about what happens if we don't. What does a 4-degree world look like? Well, most of the tropics and subtropics are going to be too hot for humans. This isn't going to affect New Zealand, but it's going to affect a lot of countries to the north. And there are a lot of people live in them. We talked about rainfall patterns changing. Sea level, we talked about that. But at a 4-degree world sustained, the sea level is going to be eventually very high, 20 to 40 meters higher, drowning a lot of coastal cities. And maximum carrying capacity, there's a lot of debate about that. It depends on how resilient and clever humans are. And some people say we can survive even 4 degrees. But I think some of the more informed people say, no, we can't, that we can support maybe 1 billion. We're not going to support today's 7.4 billion and still going up. So my colleague John Schellenhuber at the Potsdam Institute, when you ask him what's the difference between the Paris target and business as usual, he only answers in 2 words. It takes him only 2 words. Human civilization, that's the difference. So he's pretty convinced that if we go much over 2 degrees, we're likely not to stop until we hit 4 because of the tipping points and feedbacks. And if we hit 4, it's going to be chaos as people scramble to be able to grow food, scramble away from cities that are being inundated and so on. Not a nice world.